All right, so in this video, we are going to look at the differential equation which models electrical circuits, or the basics of electrical circuits. Okay, so we're going to be looking at the RLC circuit. So I have a bunch of information written down here, just so you wouldn't have to write it all out. Okay, so over here we have a circuit, an RLC circuit. So this circuit consists of a resistor. The resistor is down here, an inductor right here, and a capacitor right up here. Okay, so the resistor has some resistance of R ohms. The inductor has an inductance of L henries, and the capacitor with the capacitance of C farads. Okay, so these three components are connected in series, and there's also a source of electromotive force that supplies some voltage E of t. Okay, so this is the external force, or the voltage that's supplied. Switch up here is closed, this results in a current capital I of t, which flows through the circuit, and it also results, when the switch is closed, there's a charge of Q of t right here, coulombs, on the capacitor, okay, at time t. Okay, so that's kind of the basics of the circuit. You don't really need to understand how everything here works. The main thing is what the differential equation is, and how it's related to the differential equation we looked at before for a mass on a spring. Okay, so across each of these three components, the resistor, the inductor, and the capacitor, there is a voltage drop, okay, across those three circuit elements. Okay, so for the inductor, the voltage drop is L times the derivative of I with respect to t, so the derivative of current. Across the resistor, there's a voltage drop of capital R times capital I, and across the capacitor, there is a voltage drop of 1 over C times Q. Okay, now one of Kirchhoff's laws says that if you sum up all the voltage drops, okay, the sigma here is sum of all the voltage drops, that's equal to the applied voltage. Okay, the applied voltage here is E of t. And it's also important to know that I and Q are related by this. The derivative of Q is equal to I. So what we want to do here is get a differential equation for the current, for example. Okay, so I'm just going to move some of this up, because all we really need now is stuff at the bottom here. Okay, so let's get out our pen. So this Kirchhoff's laws is the key thing here. The sum on the voltage drops is equal to the applied voltage, and here we have the voltage drop across each component. Okay, so we're just going to sum those up. So we have the drop across the inductor is L times di dt, okay, plus the voltage drop across the resistor, plus the voltage drop across the capacitor, which is 1 over C times Q, is equal to the applied voltage. Okay, the applied voltage is the function E of t. Okay, so now it's starting to look like a differential equation, but we still have this Q here. Now the derivative of Q is equal to I, and therefore, right, the derivative of I is equal to Q prime prime. Okay, so what we can write here is we have L times Q prime prime plus Ri plus 1 over CQ is equal to E. Okay, so in most problems, we are interested in the current, okay, I. So if we differentiate this equation with respect to time, we get L Q triple prime plus R I prime plus 1 over C Q prime equals E prime, okay? And then using this relationship right here, we can write this as the following. So we have Q triple prime, okay? So Q triple prime would be I double prime. So we have the following, I'll put a line here. This is the main differential equation. We have L times Q triple prime, but Q, the third derivative of Q is I double prime, so second derivative of current, plus r times I prime. I prime is q double prime. Or we're going to leave it as I prime though, because we want a differential equation for current, because that's what we're most interested in usually. Plus 1 over c. Oh, I made a mistake there. See, when we went from this step to this step, we were differentiating, and I forgot to write the q prime here. Okay, so that makes more sense. So the q prime is equal to I. So here we'll have I. Okay, equals, and then the derivative of the electromotive force, so E prime. So that will be known because that'll be given. So that's our differential equation, which models the current flowing in a circuit, in an RLC circuit. Now notice that this is second order, it's constant coefficient, and it's linear. And also, if you look at it closely, so it's a differential equation for I, L, R, and 1 over C are constant coefficients, and we have some known function over here. So we just want to solve for I of t. Notice the similarity between the mass on a spring. So remember, this is really important. So we'll say here, notice that if we have a mass on a spring, which we did in the last video, the differential equation that we had got for the position was the following: m times y double prime plus c times y prime plus k times y equals some function of t, the forcing function. These differential equations are basically identical, right? They just have different meanings, but they're of the exact same form. They're both second order and constant coefficient and linear. And so if we can solve one equation, the methods that we use for that will be the exact same methods that we use on the other one. Okay, so this was just another interesting application of where differential equations come about. And this is a very special differential equation. Both of these are the same type that we're going to be learning how to solve in this course. Thanks.